Notice we're skipping 1.2. I'll be doing that. Friday's my plan. Okay? So this is 1.3. What page is that? 9? All right. More definition type stuff. What's the definition? What's the difference between accuracy and precision? Well, you know I'm going to tell you. Anyone guess? Guesses? What? Are you just looking in the book and saying something? Okay, I like it. Wouldn't get you a mark on a test, though. Yeah, but good.
Precision refers to the read program.
Jeff? Any doorknob can look it up in the book and repeat it.
You were asking for it?
I know, but in your own words, because that's called plagiarism. Okay, so I did a lot of golfing this year. It was wonderful. Even had an extended golf season. Okay, not that it's over, but it's getting close by the looks of it out there. Okay, so I'm on the driving range for practice. I pull out my 7-iron, which is a Ping G25, and I hit it, I don't know, 142 yards, right there. And because the range balls are quality tour level balls with urethane covers, it doesn't roll, it just sticks right there, okay? So I do it again. And I hit it right there. Okay, that's actual size. So how big's a golf ball? You guys know, right? Are they pretty close to one another? Am I good? Well, I wish I was. I'm actually lying, but all right. And then I hit another one. And it went right there. And then I hit another one. And it went right there. Is it accurate or is it precise? That's my question. I hit another one's right there. Now what do you think? You got 5 points of data here. Use your scientific brains. What's the likelihood that my next ball is going to land around the same area? Is it pretty likely or is it unlikely? Do you think this is reproducible to some great measure? It looks like it, doesn't it? The only problem is that's a sand bunker and the flag's over here. So am I good? No, I suck. Okay? But I suck consistently, right? next one, look, odds are it's going to go right there. So something, I mean, I'm able to reproduce that really, really well. But I'm not really probably going to get a low score because all these things should have been over here. Okay? So that's one example. Now, is this accurate or is it precise? Yeah, I like that. And if you already read it in the book, you might know the answer already. If I was accurate, they would be around here somewhere on the green, okay? That's definitely precise, but it's not necessarily accurate. So here's another example, and you're going to want to write this in here. I'm not even going to put words here, okay? A picture is worth 1,000 words. Anyone ever pull back an arrow and go plunk? Michael has. That's called a bullseye, right? And of course, the object of the game here is to get it as close to the center as possible. Okay, so these are notes. You guys are going to want this because we don't all have photographic memories, right? So Michael pulls out his bow and arrow and goes, whoosh. Not bad. Okay, 5 points, 10 points, 20 points, I don't know, whatever. But pretty close to the center, okay? He does it again. Not bad. Okay, he does it again. Woo! 10-pointer, even better. Does it again. He's there. Okay? Is he good? I would say so. Maybe someone distracted him and he missed, and I don't know, hit a rabbit. Okay? Now, it wasn't the object of the game, but at least he's got dinner. Okay, he's pretty good. Not bad. And then Dan comes up here. We'll give him a bigger target because, you know, because he's a blonde. And he comes up here and he goes, okay, not bad, not bad. And then he lines up another arrow. Still okay. And he lines up another one. And then another one. And another one. And you're like, wow, man. What's the likelihood he's going to hit it in that same area, do you think? Probably pretty good. Okay? Mike is accurate, but maybe not very precise. Okay? Dannon, man, that's precision. Only problem is, you know what? Maybe we just got to make a little adjustment somewhere. Maybe it's his eyesight. Maybe it's the tool he's using. Maybe you just need a better bow. Maybe you're just really, really good, but maybe every arrow is just slightly curved. Maybe you got it from Walmart instead of the, you know, Herbie Surplus. Okay? Maybe you need a better arrow. Get a quality arrow. Maybe all of those would be bullseye, dead center. But that's definitely precise. Okay? Now, are these mutually exclusive events? Can you be both accurate and precise? Sure you can, and that's what you want. You're going to score big, okay? Maybe even make some money if you're really good, like better than the rest of the world, okay? There's a couple hockey players in here. If you got a decent stick, like a good old wood Sherwood, okay? If you're Wayne Gretzky, he's accurate and precise. And they have competitions in the All-Star game to see who is the best in the league, all right? And usually, it's a guy who gets a lot of goals too, right? Because if you're really, really good with a stick, well, you can put it in that top corner, this top corner, 5-hole, and if you're quick, you're making a lot of money, okay? So yeah, this matters. Okay, they're accurate and precise. So these aren't necessarily mutually exclusive. If you're like me and you weren't as accurate as necessary or precise as necessary or quick enough on your skates, well then you're not in the NHL, you're a teacher. Okay? And that's okay. But, all right, you can have both, and you can have, in my case, neither. Okay, so that's kind of common sense maybe, but let's write it down. Okay? How reproducible is this? Precise. Are you able to reproduce it? That's one question. That's not how you spell that. You might ask yourself. Is the ability to reproduce it high? Then it's probably pretty precise. Accuracy, okay, is the definition in the book we'll just go to now. There's no point in me writing it down. So I'm going to be jumping around a bit here today. Okay? Because there's a couple things to talk about, and I like to do it in a particular order as I'm talking about it. Here we go. So as a definition, that's what the book says. The agreement of a particular value with its true value. That maybe doesn't make as much sense as maybe the picture I just wrote, right? Okay, that's why I do the picture. Picture's worth 1,000 words. Okay? This usually has to do with, not always, but usually, this has to do with the person using the bow or the tool or whatever you might have. There's some people that are good mechanics. Some people don't even know the difference between a wrench and a screwdriver, right? How good are you using your hands? You want to be a good machinist? If you don't have good hands, you never will be. Okay, this has to do with the user. Whereas precision, and they got a couple different definitions here. There's that word, reproducibility. Has to do with the tool or the instrument. Okay? If Dannon had a better bow other than that Walmart special, maybe he would have got all 5 bullseyes. Okay, it's a limiting factor. It's not precise as it could be. Right? So how exact is it? He was really exact. So was my golf balls. They were really exact. They were just not in the right spot. Okay? So maybe a pair of glasses. Now I'm hitting it at the flag. Maybe a little alignment. Okay, I just got to turn a bit right. Maybe it was windy. Without wind, maybe they all would have been right at the flag, right? Okay? Just because there's a picture of it, I'll talk about this thing. It kind of says it here. You know what this thing is? It is the kilogram to which all other kilograms on Earth are measured. It's held in a safe in France. Yeah. And it's, I can't remember, I think it's solid gold. It's either gold or it's platinum. But the reason is, like that's exactly 1.000000 kilograms. Everywhere else in Earth, before we had, to make their scale, they would take this and then balance their scale exactly to that. Now they could take their scale to a different country and measure their own kilograms, okay? Remember in Math 10 I said, well, what's the yard? They actually had it measured from the king's nose to the end of his fingertip. And then from there, they measured it and made it a brass plaque, put it in the city street so all the tailors could come out and measure, make their own yardsticks from that. Okay? Why is it gold? Well, if something oxidizes over time, it's going to change its mass, isn't it? Okay? So this is a kilogram then, it's still a kilogram now. It's in the, like I say, it's in the France Museum. Kind of cool, anyway. Okay, that's accuracy and precision. Jump back. When we're talking about accuracy and precision, we're talking about the instrument. Okay? It can only be as good as the instrument you have. Also in Math 10, remember I said, you can measure things. Some people, if you look at this ruler from this angle, I got 15.5. If I look at it here, it's 15.2. If I put my head over there, well, it's even less than 15. That's the user. That's an error. Okay? If I want to measure this thing, well, where do I put my head? It's not accurate. What's a better tool to measure something round? Thing. What's thing called? Vernier caliper. Yeah. And I don't even have to look here anymore, right? There it is. That is exactly 12.1 millimeters. Okay? There's no way I can get a 0.1 millimeter on this thing. It's the wrong tool. This is more precise. Okay? We're going to talk about significant digits. It can only have to do with the tool you're using. Okay? Sig figs. Sig digs. Okay? Is what we'll talk about right after. I may as well go here next because that's the order I have this in. Scientific notation. Now some of you guys know what this is and maybe some of you don't. Okay, what is scientific notation? That's scientific notation. It usually kind of looks like that. You want a decimal and a number after that decimal. Now I'm not going to talk about how many sig figs these things have yet because I'll do that in a sec. But because some of you don't have scientific notation yet, right on the back we're going to write some stuff. Okay, so I'm kind of flipping around a bit. Go to page 16. We're going to write some things here. Where it says scientific notation. Okay? Everybody got it? So those of you who have already done chemistry, why do we like scientific notation? Because it's what, Meryl? Did you say fun? I love marrow. Okay. It says it's a convenient way to express numbers that are really big or really small. Like, what's the mass of an electron? You guys seen that yet? Is that in chemistry?
Yeah.
You've done that, Dannon? 9.1. Is electron like pretty small? Like how many kilograms does it weigh? Like that many. Okay. Now, if you're familiar with scientific notation, you know that you want to write it like that. It's a little bit more convenient than writing how many zeros am I going to have to put in front? Not 30, yeah. But, okay, without scientific notation, 3, 4, 5, 6, 7. I'll just put 31 times. Okay? That's what it means. It's an electron, like it doesn't weigh much. How on earth did someone even measure this thing? We're not going to go there, but someone did. That's an accurate answer. Okay? Minus 31 means you move this decimal 31 spots to the left. That's how many zeros are in front of this 9.1 kilograms. It's pretty light. Okay? Here's another one. That's how many electrons pass a point in 1 second. 6.24 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17. If I put the decimal right there, that's the number I get. Okay? So, what's the difference between this number? That's really huge. This number is really small. The difference is the sign, right? That's minus, that's a positive. Here's a few examples. Okay, but they don't really have many negative ones. So, I want to write that in scientific notation. Here's how you do it. The decimal goes between the 6 and the 2. Or, more correctly, it goes after the first number. Okay? That's standard. And then I go times 10 to the, what power is going to make this thing work? Okay? This thing went 3 spots to the left. Just like this one. So I'm going to put a negative here. Okay? So negative means left. That means positive means right. Okay, if that's helpful, use it. Because it's actually backwards if you think about it the other way. But I don't know how else to explain it. This, plus you can just put it on your calculator and have it converted. Right? There's an option on your calculators to convert it to scientific notation. Okay, so here, if I want to go back, I would move this 1, 2, 3 spots, and it would be right there. This is the same number. Okay? This guy, I want the decimal right there. 6.4, but that's a significant digit, that 1. So I can't drop all that. Now how do I make this the same as that? Here's the decimal. 1, 2, 3, that's 4 spots. 1, 2, 3, 4. Okay? So positive, it goes to the right. 1, 2, 3, 4, and then that would be the same as that. Okay, that's basically the only 2 things you can do. Either you go left and it's negative, or you go right and it's positive. Okay? Is that, Reese, in scientific notation? Is that in scientific notation? No, because the decimal isn't after the first digit. It's right here, okay? Even though you don't see one, like the number 4, well, there's the decimal, okay? I want it to be there. So 7.4 times 10 to the, here it's 3. I got to go one more spot. Okay, so it's going to be 4, right? Okay? Because if I move this to there, positive to the right, this is going to be only a 3 now. So that's okay? That's pretty much all I can say about scientific notation. Any questions? All right, sig figs. Back to page 9. All I want to point out here, there's some examples. If after the next half hour you don't really get it, read this, okay? Like read it all. Should I say that every day? Or can we just like figure out we're Physics 11 students and we should just read it? Okay? Page 13. Told you I'd be hopping around a lot. Okay. Sig figs. We got to add and subtract measurements. Okay. This example, someone measured this and they said that was 1.756 meters long. It's only accurate to that 6, the last number. And that's due to the device they're using to measure it. Okay? If I'm using my feet, if it's like 8,000 years ago and I don't have rulers or anything, then that's going to be like plus or minus my foot. Maybe half a foot. That's as accurate as I could be. Nowadays, it's a lot more precise. Okay? But it's due to the instrument you're using. So this is the 10th spot. That's the 100th spot. This is accurate to the 1,000th spot. Now the last one, that could have been a 5, it could have been a 7. Okay? That's only as accurate as we could get. Now we want to add something to it. These things I know are 2.2 millimeters. That's a different unit. All right? So that's 1/10 of a millimeter, but if I make it meters, it's 0.0022 meters. That's tenths, hundredths, thousandths, 10,000th spot. Right? That's okay. I used a different instrument to measure those. It's more accurate. Okay? Everybody with me so far? That's accurate to the thousandths. That's accurate 10th, 100th, thousandths, 10,000ths. This is more accurate, isn't it? All right. So, someone's making something. They're taking this measurement and they're adding on one of these on one side of it, and they're adding another one on the other side of it. Okay, they're making this desk in front of you, right? You got the middle part, and then you got 2 pieces of oak trim around the outside. Okay? When I add these, okay, and I have thousandths and then 10,000ths, and I add them up and don't even think about significant digits, my answer is 1.7604, which is 10,000. So the question is, how does that make sense? Because this first measurement is only accurate to the 1,000th spot, and just because I add 2 things to it, it doesn't get more accurate. Okay? I cannot have this thing accurate to the 10,000th spot. It can only be accurate to my worst measurement. Does that make sense? So I have to get rid of that 4. That's what this is saying. Okay? It's only accurate to the 10,000th spot. So that 4 is meaningless. Doesn't make any sense at all. Okay? So in the rules, it says this. Anyone want another example? I'll do it anyway. You like money? Okay, someone worked in the summertime and the guy says, I'll give you about $100 a day for your work. Okay? All right? Maybe some days I'll give you 90. Maybe some days I'll give you 110. Okay, so this is plus or minus $10. Okay? It's $100 plus or minus $10. Now you work 2 days. So it could be 90 and 90, or it could be 110 and 110, right? So that's now 200 plus or minus 20. So I'm adding a day to another day. Well, would it make sense for you to work 1 day and have it plus or minus $10, and then work 2 days and have it plus or minus $5? Does that make any sense? It doesn't. How can it be more accurate the longer you go? Okay? The more things you add to this, how can it be more accurate? It doesn't make any sense. I don't know if that example helps, but I don't know. Okay? Use it if it does. So that's kind of an explanation of it. Here's the actual rule. And don't worry, I'll give you something else. When you add or subtract measurements, the sum or the difference will have as many digits after the decimal point as the one measurement with the least number of digits after the decimal point. Okay? So, like I said, this thing was only accurate to the third decimal, the thousandth spot. You don't even have to know thousandths and 10,000ths, okay? You just need to count after the decimal. These were accurate to the fourth. That doesn't make any sense. It can't be accurate to the fourth. This is my least accurate measurement, so my answer can only go to 3 decimals after. So all you do is add them up or subtract them, count the number of decimals in the least measurement, and then round your answer to that. Okay? Make sense? All right, a couple of examples. I can almost read this. This is 4021.7. That's only accurate to the 10th of a centimeter, right? It's either 0.7, 0.8, or 0.6. They said it was 0.7. How can I add this accurate to 0.089 centimeters, which is like 8.9 millimeters, which is a lot more accurate than this, and have the answer be something even just as accurate as this one, okay? It doesn't make any sense. So here's what you do. 4021.7. Just add them together, 0.089. And that gives you 4021.789. But what's the least accurate number I have here? There's only 1 decimal after the decimal spot. So this answer can only have 1 decimal, okay? So this 9 makes this 8 a 9, and that makes this 7 an 8. It can only be to the 10th spot, okay? All right, make sense? Same thing here. I got 2 decimals, I got 1 decimal. This is the least accurate number, only 1 decimal. So my answer only has 1 decimal. All right? Now what happens if you multiply or divide? Different rule. I'm not going to give you an explanation here. I'm just going to give you the rule. Okay? You're going to multiply. Someone measured this wall fairly accurately. It's not 8 meters. It's not 8.5 meters. It's 8.53 meters. Another wall was 2.74 meters. 100th of a meter these are accurate to. How many centimeters is that? It's accurate to the nearest centimeter, right? There's 100 centimeters in a meter. Okay? So anytime you're going to multiply, well, the last digit is uncertain. It could have been a 2, could have been a 4. They just took the average and put a 3 here. So anytime you multiply with that, the rest of them, like how can I get something that's all of a sudden accurate to like 1/10 of a millimeter? Doesn't make any sense. When multiplying or dividing, the product or quotient must have no more sig figs than the single measurement with the fewest significant digit. Okay? This thing has 3 significant digits. This thing has 3 significant digits, so my answer has to have only 3 significant digits. Not 1, 2, 3, 4, 5, 6. Doesn't make any sense. Just because I'm multiplying doesn't mean all of a sudden my tool got more accurate. Okay? Right? Like it doesn't make any sense. So rule's a little bit different. You're counting up sig figs. All right? Now, do you know what sig figs are? Significant digits. First of all, an example. There's 3 there. There's 3 there. Okay? I want to round that to 3 sig figs. So don't think addition and subtraction. Don't go there's 2 after the decimal, 2 after the decimal. This one only has 1 after the decimal because I got 3 sig figs. Significant digits. Keep calling them sig figs. All right? That's just what the rule says. There's 3 there. There's 3 there. So my answer has to have 3. Not 1, 2, 3, 4, 5, 6. Okay? Okay? So the only thing you may not know is, how do you know looking at a number how many significant digits it has? What if you get this number? How many significant digits does that have, Dana? Okay, do kids who haven't taken chemistry know that? I have another sheet here for a little bit of review. If you're in grade 12 and if you're in grade 11. And we'll just look at this for a second, okay? Okay, because like I said, in this class, the hard part is kind of hitting the middle of you guys. Without boring the grade 12s, but not making it too hard for the kids who haven't taken Chemistry 11. So, where is that? Significant figures. Blah, blah, blah. Rules. Zeros between other non-zero digits are definitely significant. Down here, there's examples for rule number 1. All you do is count up the numbers. That 0 has to be significant here, okay? Because it's in between other numbers. So how many sig figs do I have? 1, 2, 3, 4, 5, 6. Right? Same thing. I got 4. All you do is count them up. These are all significant digits. They all matter. Okay? So for example, 4,005. Someone actually counted, say, 4,005 centimeters. Not 4,004, Not 4,006, 4,005. It's accurate to the nearest centimeter. Of course, that 0 matters. It's not 4,105, right? So that's not a bad one. That one's pretty easy. Rule 2. Zeros in front of let me read that again. Zeros in front of non-zero digits are not significant. Rule number 2. There's an example. These are not significant. All these do are tell you where the decimal is. Okay? So someone measured like 45 of something, but then they converted it. And in order to convert it, they have to move the decimal over to here. It doesn't become more accurate just because they converted it. These are not significant. There's only 2 sig figs here. Right? There's only 1 sig fig here. There's only 1 significant digit here, just the 9. The rest just tell you where the decimal is. Right? Does that make sense? Rule 3. Zeros at the end of a number, but also right to the decimal are significant. Okay, what? We got to look at that. 58.00. Just ask yourself, why are those zeros there? They have to be there because someone was that accurate. It wasn't just 58. It wasn't just 58.0. It was 58.00. Why would they write those zeros there if they didn't matter? Okay? That's accurate to the 100th of a, I don't know what, micron, meter, foot. Okay? Same thing with this. Accurate to the 100th of a something. Okay? 7.00 nanometers. That's it. Accurate to the 100th of a nanometer. It's really, really accurate. Look at that. Okay? Why would they write all those zeros if they didn't matter? Okay? Same thing. So how many sig figs are here? 4, 3, 7, 5. Okay? There's 5 sig figs here. They're all significant. They all matter. Got it, Sarah? All right? The last one is the weird one. End of a number, but left of the decimal. Okay? Is that 0 significant there, Dannon? Trick question. It might be. We don't know. Okay? That might be accurate if it's 250 kilometers. Maybe it's accurate plus or minus 10 kilometers. Maybe it's accurate to the nearest kilometer. Maybe that's not 251, it's not 249, it's exactly 250. Okay? But it might have been maybe plus or minus 10K. Okay? It might have been 254, but not 260. The only way you know is to ask the person who did the measurement, because you don't know how accurate the tool was used that they did it with. Okay? So that's the weirdo. Is this accurate? How many sig figs? We don't know. You don't assume it's 3. You have to assume it's 2, because you didn't talk to the person who did it. This might be 4 sig figs. It might be 3. It might be 2. It might be 1. You don't know. So if you don't know, you just say it's 1. Okay? Does that make sense? So that's sig, figs, basically everything you need to know about those if you don't already. And I'm sorry if you're really confused because you just came out of grade 10. All right. All that's left is the assignment. Lots of stuff. Okay, so first, accuracy and precision, just a couple of questions. Oh, when I got answers, who has a red book? The book with the red line in the front? Okay, I got full sets of answers for you, so you can check yesterday's odd ones. So you only had one answer. You only had number 2. What about number 1 and 3? Now you can check it, okay? So that first. Now what do I mean page 14 to 17? Those, that's page 14, okay? Those, that's page 16, and of course 17 look like real assignment questions, okay? So all, one exception, because otherwise you'll pull your hair out and come screaming to me. Don't do 3C on page 17, okay? So all except 3C. So I don't really agree with the answer too much. And I haven't taught it yet. It's going to be tomorrow. Unfortunately, you know, sometimes we go a little bit forward before we can go backward. Units. Okay? If you multiply meters times a meter, what's your unit? Meters squared. If you multiply milliliters and grams per milliliter, what's your unit? Tyrell? Milliliters on the top, milliliters on the bottom, just grams. Okay? Get in the habit of doing it now because it'll cost you marks if you don't. Okay?